Yes, and we're being recorded, so I'll try to behave. First, one slide of this. I'll have to get used to this. Chalmers, if anyone wonders, is in the southern tip of Sweden in Gothenburg. This is the downtown Gothenburg area. It's actually well worth a visit if you're around. And here's the chemistry department where I'm in. So this will be, as Ross said, I used to do both theory and experiment. Nowadays it's only theory, and this talk is about modeling compression on very small systems, and this is a long story. I will only talk about the last chapter of this long story, but it started in Cornell when I worked with Roald here and Neil. Magnus and in Paul Ehrhart's group. No relation to Magnus here, just one of the few other Rahms in Sweden. So, well, this is a motivational slide. I think you're all quite aware why pressure is interesting. We are also looking into astrochemical studies in my group, and we have not started doing so under high pressure yet, but it's just fascinating to me how it's such an interesting orthogonal dimension in chemistry, but also maybe especially in materials. This is a slide I took from this recent very good paper, I think, by some friends. This is where it started for me. I got realized that under pressure, we could basically take our chemical intuition and throw it out the window. This was a bit frustrating. I still sort of am. I mean, we have all of these really odd structures forming, and we have hydrogen clathrates and nitrogen polymerizing in ways that are not stable under normal conditions, and you know, all sorts of peculiar things. And I realized then that the reason why it's weird is just simply because it's a different thermodynamic condition. It's not weird if we had been used to this. And the way that we make sense of things, at least in the first sort of 0th order approximation, is using very simple rules, atomic properties. For example, that's usually where I start, at least. Electronegativity, atomic properties, volumes of atoms, polarizability, things like that. And they don't exist for most, at least they didn't at the time, not very well, at least in under high pressure conditions. So that sort of started then the quest of fixing that issue. The last part of this story is the van der Waals radii. Why do we care about van der Waals radii? I am guessing we have a mixed audience here of physicists and chemists, so excuse me for I'm going to try to balance it, but I think most of us are aware of what they're useful for. And also I have to excuse this. You have to excuse this. I know the scale is wrong in this picture of the atom, but I thought it looked cool. Van der Waals radii are useful for very many reasons. I mean, first of all, you can look at the crystal structure and just immediately say, you just measure the distance between two atoms, and then if the sum of if that distance is shorter than the sum of the van der Waals radii, then you immediately know that there's probably some interactions and bonding interactions between these atoms. So you can essentially infer electronic structure and properties and stability to some degree using just knowledge of also covalent and ionic, different kinds of radii. You can also, I mean, what they're mostly useful for also is just getting an idea of how large things are. How big is a molecule? Where is a practical end to the molecule? Is that the van der Waals surface? And these are very common also in various For example, if you look at enzymes or biological molecules and you want to color some property, electrostatic properties on the surface of a molecule, the surface you will use is the van der Waals surface. Also useful for obtaining free space in materials and things like that. So the big challenge here is, of course, that they have been missing for high pressure. So leading to the confusion I mentioned before. And this is the motivation for this talk that I'll be telling you today. I would like to stress here that these radii, they are very much different from bonded radii. Of course, there's a lot of extremely impressive experimental work and theoretical work on equations of state, compressed matter of various sorts. But what you typically get out from those materials, if they're not noble gas elements, are bonded estimates to sizes of atoms, if you were after that. It's actually, I mean, of course, there's a lot of equations of state published. The only place we found where there's actually explicitly tabulated radii under pressure, there might be one more I've forgotten here actually, but it's one from Royce in 67, where you've explicitly tabulated them. So this is where we had to start. First, we had to actually revise the entire periodic table and calculate the radii of the atoms at 1 atmosphere. The reasons for these are many. Maybe my helium is not showing here, but I think you'll be fine without helium. The reasons for this were many. One is that will become clear in the next slide. Another one is that the ones that were existing, the scales of van der Waals elements that van der Waals radii that existed weren't as inclusive as we wanted, or they were not so systematic. So this is nothing new here on this slide. They behave as they should. The units are in angstrom. One possible weird thing here, the one arguably weird thing is that the second row here or group are larger than the first group, and this is actually the case in this definition. Anyway, these sets of radii corresponds extremely well with crystallographic estimates to the same thing if you look at statistical analysis of crystal structure databases. So how did we get to these radii? Oh yeah, before I say that, if you're wondering what are the most average elements, we Swedes, we're very much not too special. We like to be very average, so I'm giving you the average atoms here. Radon has the average size, and sulfur has the median value, or palladium possibly. So this, as you will see, will change under pressure. So the way we got these reference values, 1 atmosphere, is that we define the edge of the atom by an electron density cutoff. Simply this value of 0.001 electron per cubic Bohr. This is in a region where the electron density decays exponentially. So here you see a natural logarithm of the electron density for 2 atoms as a function of distance. Somewhere here in this flat region, we cut off. This specific value was actually suggested by a man named Boyle a long time ago. It's commonly used when chemists wants to plot some property on the surface of an atom. Turns out that this value just was the right value. We tried a few others, which is rather remarkable in itself, actually. So it's a quite simple definition based on electron density. Okay, so that's how we get started. And now the question is, what happens to these poor radii under pressure? And we're going to look at that between 0 and 300 gigapascals. And basically everything, almost everything I'm going to tell you here or show you is summarized in this article that was published only a couple of weeks ago. So you can go back and look at it there if parts of, for example, the method part here that I'll be addressing is too short, or if you're interested in anything else. the compression model we have, I have to spend some time on this because otherwise it'll be a bit confusing. What we do is that we consider a single atom in the ground state. Excuse me. And then we put it in a spherical cavity. The cavity is defined by a boundary, which is at which point there is a step potential. And this is one of the parameters of the model, the height of this step barrier potential. And outside the cavity, there is a low dielectric continuum. You can think of this as a homogeneous electron gas. It's only defined by two things: the electron density of the electron gas and the dielectric constant of it, which is low. So as we will see soon, this surrounding, the closest physical correspondence to it is isotropic neon. So it's a non-reacting, inert, but chemically reasonable surrounding. So in the cavity, the size of the cavity is defined differently for each atom. So they are scaled from their van der Waals radii, and at the starting pressure, which corresponds to very near zero pressure, we have used a diameter of this cavity that's 30% larger than what's given by the van der Waals diameter, van der Waals radii. And I'm going to get back to this. This is simply a value. There's nothing magical with this value. It's a value that we use together with our settings for the surrounding and the setting of this barrier height, so that the first calculation corresponds to very low pressure. Then the energy of this system is then calculated using a Hamiltonian, and then of the unperturbed system. And then we have two terms more here that describes the electrostatic and the polar repulsion. Basically, the mediator of the pressure in this case, the interactions with the surrounding environment, and they can penetrate this barrier then. The beauty of this method, which I should also state what it is, it's called the XPPCM model, extreme pressure polarizable continuum model. That one has been developed for a few years by Roberto Cammi, who is a collaborator on this paper I just showed you and we're presenting here today. The XPPCM model is basically a bootstrap of a very well-known method in chemistry, the PCM model for implicit solvation modeling, but here it's used instead to model pressure. The way that pressure is calculated is that we calculate the total energy for this system at a given diameter for one atom, and then we shrink the cavity size and recalculate the energy for that smaller cavity. And then the pressure here, the microscopic pressure of that atom, is the derivative of the total energy with respect to the volume. Yeah, the beauty of this method is that you can apply any level of theory in principle. We actually started doing this with coupled cluster theory, but since we're doing full potential calculations, so all electrons are included for even uranium and things like that, we have decided to go for hybrid GFT calculations, and these are, for those interested, relativistic calculations then, and one issue or one possible caveat that we have here is that the basis set, ideally we would want to optimize the basis set. These are atom-centered basis functions for each of these cavity radii, but we can't do that because it would take too much time. So we have simply relied on the largest basis set in existence, this ANO RCC basis set, which is available for the first 96 elements. So it's a level of theory that I would say would be very hard to do in the codes that we normally use for extended systems, real crystals, VASP and the quantum expressor and these things. We could in principle do multi-reference calculations here as well. Okay, so that's the method. I'm going to come back to some validation of it soon. One slide on sort of the crowning achievement that I wrote together with Roberto, Neil and Roald last year, and that was sort of what we first aimed at, which was to obtain electronegativities of the atoms under compression. I would not be discussing this today. but also and also discuss how the electron configurations of the atoms change under pressure. We will mention that briefly. But in short, what happens here is that if you permit me to have a little pictorial view here of a potential around an atom, and then we have different quantized energy levels that are occupied in some fashion. And in this previous work here, we then defined the electronegativities, the average binding energy of these, the average energy of these occupied levels. And then what happens on the compression, real compression, or this model compression, is that we effectively take away part of this attractive potential. And as a consequence of this, the energy levels will go up. The electrons will become less bound. They can even become less bound than vacuum. They can have positive energies here, but they're contained. You can rationalize from this from a shrinking box and increasing kinetic energies also. And then in this situation here, you have the energies of the electrons they're higher up, they're less bound, so the electronegativity will be different, and we could calculate how that changes. And also the nature of these orbitals, the nature of the ground state can change fundamentally. Okay, but we will talk about volumes here today. So one of the first method validations we did were to compare two noble gas elements, the equations to state for noble gas elements. And this is the volume divided by the volume at 1 gigapascal in the method, and the experimental values are the crosses here. So we could reproduce this very well with the model. So that was promising, and that was sort of how we moved on to predicting electronegativities and things like that. Which that was a lot of fun, and there's a lot of fun predictions of that. Maybe I'll come back to it if we have some time. Even some simpler metals, actually, this might be fortuitous, but this is the equation of state for potassium. You see some little drop here in the volume at some pressure. We see the same thing in the single atom model at higher pressure, and we could explain this by this ground state change in the electron configuration from 4s to 3d of potassium. But since it worked so nice for noble gas elements, we in the last chapter here of the story, we decided to check if we could actually backtrack out radii from this that mean anything. So I'm going to go through. This is the last slide with some equations. I hope they will make sense. So what I showed you before was the equation of state, which is essentially this: the molar volume at 1 pressure divided by the molar volume at 1 gigapascal, and how this related very much to the cavity radii we had that were scaled up a bit. So that's the same thing, just rewritten. I mentioned that we had the scaling factor was 30% larger compared to, we took the atmospheric van der Waals radii and scaled them up by 30%, and that's how we had our initial cavity radii. And these correspond to very low pressures. So because they correspond to very low pressures, we equate this equation and replace 1 here with that scaling factor and 0 instead. Well, long story short, then you can do the same analysis over the radii and relate the cavity radii to the experimental radii and the previously tabulated van der Waals radii. And what I'm saying here is that the radii we will present here as the van der Waals radii, or non-bonded radii under compression, they are the cavity radii that we used in our model divided by 1.3. So we're just scaling back with the same factor as we initially used. So it's not too complicated. And if we do that, we have an excellent agreement with, again, experiments. The experiment here, this is for the noble gas elements. The experiments here, how do we get radii from experiments? It is through assuming a perfect packing, in which case we use this formula. The volume here is the molar volume, or the atomic volume of the atom, and then in a perfect packing of hard spheres, here you can back out the radius. So this is how well it agrees, and if you just sort of eyeball this, then it seems like our model is closely resembling neon, as I mentioned before. Then we put other atoms into this model, and then you can consider them as being other single atoms in a sea of isotropic neon. That's hard to do experimentally, arguably, right? So what I'm maybe not impossible. You could dilute atoms and compress them in neon, but what we're talking about here are not compressed real materials, but really single atoms in neon. So it is meant to be a reference for single atoms under compression. One last slide here. This is where we compare these radii that I'll soon show you with the metallic radii compiled by this guy Royce a long time ago. These are from shockwave experiments. Basically we have an agreement here. The metallic, these are from the Wigner-Seitz definition of the radii at 100 GPa. They are slightly smaller. The bonded ones are slightly smaller, which they should be, since ours are non-bonded. And this is a first look at three pressures. Then the top curve here is the normal van der Waals radii we know and love. Below here in blue is our predictions for 100 GPa. White crosses are the Royce experimental radii, metallic radii, bonded radii, so they're slightly smaller. Usually you have similar trend here, and then 300 GPa in red. So I'm gonna walk us through a few examples, or most examples in a bit of a brutish way, and then we'll look at some relative comparisons. Beginning with the first row, helium to neon. This is, I hope you all see, it's always going to be size on the y-axis and pressure on the x-axis. You know, I mean, the takeaway here is that, yeah, under pressure, atoms are still very much different. I mean, they still very much differ. We have some element, in this case lithium, that changes order. It becomes smaller than carbon and boron and beryllium. And there's something funny going on here at one pressure. So yeah, that's just what I said. Already here we see that things are still very much different. They're all not the same at high pressure. And okay, so in this picture I'm showing you the same thing. Lithium here is in red, and we have this little jump down here, this volume decompression or decrease. Here's potassium for some reason, showing the same but the larger decrease, and then we have sodium in blue and hydrogen in light blue. Yeah, lithium, this little compression here in lithium is or volume decrease in lithium is actually rather unique. It seems like in our model, lithium is the only element that by itself in isolation, again, without any chemical bonding, can turn into a p-block element. So that doesn't happen to anyone else, even when we take our model way beyond where it's been validated. Much more common is what happens in potassium, and that's the one I showed you before, when we have 4s1 to 3d1. We have a S to D transition, yeah. So why do they happen? I think you have heard this before, but if you have not, this is rather straightforward. You start with an electronic configuration of the atom. That in the case of potassium is 4s. So this is a rather voluminous wave function. It spreads out a lot in space, and this means that it interacts rather strongly with an interacting environment, especially when that environment presses up upon it. So this electronic configuration will go up in energy faster than the excited state, which corresponds to the 3D occupation. And at some point, the enthalpies of these two states will be the same. The electronic energies will not be the same, but the enthalpies will be the same, and this is due to the added pressure work term. And at that point, there will be a switch, and then typically the smaller wave function here, which is the 3D in this case, it's physically smaller, less spatial extent of it, will win out. and that's why we have this sudden jump in volume for a single atom. So to which degree this exactly happens in a bonded material, that's you know, obviously it's more complicated when you throw in bonding as well, and that's something we're very interested to look into. So I should mention here also that typically these this is a 1 electron transition. Typically they are about 0.1 angstrom, independently of pressure, if they go from S to D. So what is 0.1 angstrom worth in energy? Well, if we translate that to, or rather, this dashed line here corresponds to the average atom. The average atom is 1.48 angstrom, as I mentioned, and at 100 GPa. That's the size of the average atom. Now, if you change the size of that atom by 0.1 angstrom at 100 GPa, that corresponds then to about 2 electron volts. So rather chemically significant. If you have half the size of that change, then it's about 1 electron volt. If you have the same change, which we do see in some elements, the same 0.1 angstrom change due to electronic transition at 300 gigapascal instead, then this is worth about 5 eV. So these small changes in the atoms, they become more and more worth, so to speak, in energy. And yeah, so we can keep that in mind as we go through these remaining slides. This is the first, this is the third row. Not too much happening here. We have sodium coming down a lot. It's much more compressible as it should be. This is what we see in the real material. And the differences between the atoms changes more and more, or they disappear more and more. Magnesium is also more compressible than the other ones. This is the second, this is the alkaline earth atoms. Apologies for this rather complicated plot here. I'm going to end by giving you a tool so that you can look at your favorite 2 or 3 atoms and compare them in the same way. So I mean, the only thing we can say here is that we have these small transitions that correspond to about 0.1 angstrom, as I mentioned, or slightly below. And then we have larger ones that are due to 2 electron transitions. So 2 S goes to 2D here. And they are just really close to each other. We couldn't really distinguish if it's 1 or 2 if it happens at the same time. In our model, it seems to be occurring at the same time, whereas here for the heavier ones, some of them they have them spread out. Okay, the heavy main group, these guys over here, not too interesting actually. This is not the greatest figure. All I want to say here really is that these rows, they go together. You have very minor, sure, they rearrange in size relative to one another, but you know, typically they just go with the row like this. So that might then imply that in this region we can trust our chemical intuition a bit better. There's less dramatic things happening. The D block, first row here, it gets complicated. So we have multiple of these transitions. They are all S to D, like for potassium, but essentially the D elements, they lose all their S character when they're not bonded. So the S will go above the D and become unoccupied, and then they will of course later be involved in bonding if you put these atoms next to each other. But you see you have a larger difference between the atoms in the beginning here, and then you have a region where there's a lot of things going on, multiple electronic rearrangements, and then it sort of flattens out after that. You have nothing happening really after 200 GPa. In row 5, it's similar. The last transition here in this is molybdenum, fairly hard element. And in the last D block row, it's also a lot of things happening. I put in lanthanum here because you could argue that it could possibly fit in the D block here, and it really stands out, right? It's a much larger element. Yeah, so in this region here, after these first transitions, they have all lost all of their S character. So it's a D3 metal in this region here. The last one is osmium, another hard element. And going then to the lanthanides, the F block, I have to admit, is the hardest one to compute, obviously. So these are the ones that we believe the least, but I think I still believe them to a decent enough degree. We have a lot of transitions here. They can be up to 3 for one element, and here we also start seeing D to F transitions. So F orbitals are slightly smaller than D for the n-1 if n is the quantum number wave function. So they start to happen as well. I think, yeah, we have one for cerium here. That's the last. This is the last transition, the one at the highest pressures, as we can tell. And that is a D to F transition, I believe. For the last part here, the actinides are even more complicated to do, and here we actually had to omit 3 elements because I could not converge these calculations sufficiently well to present them with my honor intact. So there's only 5 remaining, and after this the base is set, and basically the orbital approximation breaks down. So we don't really care too much about those elements anyway. They are very short-lived. So this is the data I'm showing you here, absolute values, which are a bit hard to take in, but fear not, as I mentioned. Yeah, we might also note here that these D to F transitions, they are much smaller in size compared to the D to F. Sorry, the S to D. Yeah, so some transitions matter more than others. And I guess these are the only ones we expect to survive at even higher pressure. So our model goes up to 300 GPa, taking it even higher. Than the only thing left to do really with the periodic table is to transition all the D character away from the valence in the F block to F. And it's a bit close call to what degree that will happen, because they're very, very close in size. So let's take some few slides with relative changes instead. So this then it can look much more dramatic. So this is a comparison between iron and silicon, just 2 fairly important earth-bound elements. So if we look at the absolute values, then iron under normal conditions are 2% larger than silicon. So that's the stuff that we have near the Earth's surface. At higher pressure near the core, not that there's too much silicon there as far as I know, but anyway, then the iron atom is 8% smaller instead. So that's already fairly big change, even if you just look at the absolute change. If one looks at the relative change, then you know, this is a 150% difference here. It's 0.05% larger here and 0.1% smaller over here. And yeah, I'll show you how to plot these things in a bit. This is another example. Nickel and palladium. Nickel, of course, being above palladium in the periodic table. There's a dramatic change here. Exactly when this happens, it's not going to be like this in a real metal alloy, but this change in sort of the reference state of the atom might be an explanation for some phase transformation, possibly. I have not looked into this system. I just kind of picked out 2 elements here. What is clear anyway is the trend here. There's one becomes smaller than the other. It's opposite on the pressure. And then it can also be not very dramatic at all. This is hydrogen and carbon. So I know some of the in the audience here are very interested in that, carbon nanothreads and so on. And here really in the model at least, we see after the first 20 GPa, there's basically nothing happening. These 2 elements, they go together. So in that sense, you wouldn't expect anything to happen purely by the active compression after 20 GPa. But of course, there's electronic structures and all of that, chemical bonding again. But as far as the atoms are concerned, not much happens. There's a few other ones we can, I could have showed as well, but this is how it looks at 300 GPa. So this is the periodic table with the atomic radii. And you see here that the range from the biggest to the smallest is much smaller. But there's still a pretty important differences. And as I mentioned, the size does matter. The energy counted, small differences mean a lot here. Radium is the largest atom, and this is how it looks under normal conditions. We can go back and forth a little bit, atmospheric conditions. And then I believe it's barium or something that is larger. For various reasons, this changes a lot. So this is how it changes. I think I'll end almost soon here, but the good news here, I hope, is that we have concocted an online database or application where you can see the periodic table and dial in the pressure that you're interested in, and get these properties of the atoms, either electronegativity, which I haven't talked about, relative electronegativity relative to ambient conditions then, or these radii, or also spin of the ground state as a function of pressure, or you dial in it and get it for a given pressure. You can export this data and you can plot one element relative to other ones as well. So this is basically what I wanted when I got into high pressure chemistry, and that was missing, and I really hope that you'll find it useful. We aim to explore it to get ideas, what could be stable, which alloys could be, which atoms are, which switches can be expected. So yeah, so you can find this database here, and play around with your favorite elements. I think I'm gonna, the one little last teaser here is using that database, and you can plot things like this. This is the electronegativity of iron relative to silicon, and over here you have the radius of iron relative to silicon, and you see that the electronegativity and the radius, they go very much hand in hand, as you expect. I mean, these are smaller atoms have higher electronegativity, and this you can rationalize in many different ways. But here we've actually quantified this for essentially all of the atoms. And furthermore, a really cool thing, I think it's a really cool thing, is that you actually have these points near these transition pressures where an atom actually have two well-defined electronegativities up here and down here, and two well-defined volumes at the same time, or radii, and they also have two well-defined energies at the same pressure. So we have actually been able to relate these two very central concepts, radii and electronegativity, and also energy, specifically in these regions where you can flip between two electronic states. I'm having a little bit of trouble publishing that at the moment, so this is just a teaser, but I hope it will be forthcoming soon. So I think these are neat because you can use pressure to kind of as a key into chemical concepts, or new connections between them, or rigorous connections maybe. So the conclusions of this is that we have talked about non-bonded radii. Non-bonded is basically the same as van der Waals. I mean, the only difference would be that van der Waals radii, then you have weak dispersion interactions as well. Here we have purely non-interacting or repulsive interactions with the surrounding environment. So it's a slight difference between non-bonded and van der Waals, if I might have used both. Yeah, we have, it's pretty obvious that the atoms are very differently sized with pressure, and quantified that. Ground state electronic configurations, they do matter, at least for atoms. They matter for the size a lot. And we hope that these radii may be useful in high pressure research for experimentalists above all else. Possibly as like a first approximation to an explanation to why you have a phase transformation, why something is stable and something is not. It's estimate free space, even maybe get an idea of what's molecular, not how molecular is something. Basically, what you use van der Waals radii for under normal conditions, all sorts of things. And then we have this atoms under pressure database, yeah. So forthcoming will be using this as a key to unlock chemical concepts. And all I have been talking about, more or less, is in this paper, non-body radii of the atoms under compression. I would also like to recommend, if those of you are interested, haven't seen this one, this was a heck of a lot of work to establish the wave functions that we used in this work, the squeezing all of the elements of the periodic table from last year, and then also another little neat paper with Roberto, Roald, and Neil, where we sort of have a 0th order approximation and explain changes in electronic configurations from the spatial extent of orbitals. So that's a little bit more theoretical, but hopefully a fun read. And that was it. I hope you have some good questions for me. Thank you.
Thank you very much, Martin, for a very clear, very nice talk. I certainly hope the follow-up work gets published soon. So good luck with that. We already have some questions in the chat box.
Yeah.
Unmute yourself. Jay Kleppeis, do you want to speak up?
Should I read the chat maybe?
Yeah, okay.
Why thallium's behavior is different from other in the group of on page 28. Yeah, I can't tell off the top of my head here because, but let's go back and see. 28, you said. Or is it titanium you probably meant here? Yeah. It's not, yeah, they're all different to each other, so I would have to have a clarification here. But what happens is essentially that there is a 2-electron transition where the titanium it begins with a 2s valence, I don't misremember, that in one fell swoop here becomes a D4 element. So over here it's predicted to be D4 elements, and over here it's a S2 D2. Yeah, you can get all of the details for all of the elements in the app I showed also, so we can look at that if you want. Next question was, yep.
Yeah, sorry, I cannot find the page number, but it was about the group of 3 plots, and the far right plot is thallium, lead, bismuth, 6 elements to calculate together, and only thallium gives not smooth curves. So I expected that is where the kink is.
Oh, I see. Okay, right here. So can you still see my mouse pointer?
Yes.
Yeah, okay.
Yes.
That thing. Okay, I understand. Yeah, there is that is probably interpolation issue. There's nothing funny going on here though electronically. So some of them just have small humps like that, and it is not due to an electronic change per se. This is to say I don't particularly know, but we've looked into detail on other ones that have similar things, and there was nothing wrong with the wave function. Calcium has a really weird bumpy behavior, even though nothing really happens, for example. So it, as far as you trust the DFT, it seems to be, well, I can't really, but it's a good spot.
Yeah. Oh, and another question about, I may miss when you talk, but on the page 36 and 38, when you show all the color of the elements upon your calculation, how the ionic radius changes, neptunium and uranium and thorium didn't have any color. They are white. What they mean?
Yeah, so this is because thallium, uranium, and yeah, they are omitted. So I could not actually converge these elements in the compression calculations well enough. So
Okay.
it was just a real pain to get these last elements to work.
Okay.
So that's why, yeah, they are missing from the database. We only have data for the 1 atmosphere for them.
Okay. Thank you.
Yeah.
Thank you.
Thank you.
Urshan, Alp, do you want to ask your question?
Yeah, thank you, Martin, for this very informative talk. I learned a lot, actually. I was particularly interested in experimental observation of these collapse of the electronic size, let's say. So there is one indirect way to measure it, but in a very reliable way, is the isomer shift of the mesopar transitions, because they are very sensitive to pressure and to atomic radii, as well as changes in the shielding that is caused by this rearrangement. So I saw many elements in the periodic table which can be used, like krypton or iron or tin or uranium, to monitor these changes. Although some of the pressures are, like above 100 GPa is becoming more and more routine in more recent years. So I was wondering if you have any chance to compare. For example, in iron, you have this 20 GPa big collapse at around 20 GPa, which is related to BCC HCP transition. But the one at 150 GPa is quite interesting. Nobody has looked at that. So if you could calculate isomer shift, we could measure it. So that's something that will be very interesting.
Yeah, that is very interesting. I have sort of assumed that one would need, yeah, we can talk more about it. Maybe send me an email. It is only a model of a single atom in neon here. So the exact 150 GPa is, I would say, is not really, I wouldn't expect it to necessarily happen something in
right, but it's a substantial change, and the changes in the earlier pressure range has been observed, so one can compare. We have those values up to 25 GPa, for example. We have isomer shift values, so it would be interesting to compare, actually.
Oh, absolutely. Yeah, no, that would be.
I'll send you an email.
Awesome. It's a theorist's dream to actually have something confirmed, especially now that I don't have a lab of my own. So.
Okay, thanks.
Thank you.
More questions?
There's a few more in the chat here.
Hello, Nilesh here. I'm a postdoc from UIC. I have a question regarding the atomic radii when it is in a binary or ternary compound form under compression. How it is behaving with respect to your studies here?
That is a good question, and that's something that would essentially have to be, you'd have to compare these data, which are for non-bonded. We have no consideration of crystal structure here or composition. So this is for experimentalists to compare. Essentially, it would be very interesting to see to which degree neighboring atoms that are bonded fit with this.
Okay.
I have a follow-up question.
Yes.
Can your data be used for generation of pseudopotentials under pressure, and then these potentials to use for calculation of solids under pressure?
It's a good question also. I mean, it gives you one idea of the size, so it should give you one idea of how large the core is in a way, which you need for a pseudopotential. So maybe it could be at least a parameter that you can have a rough idea of how large. I'm not an expert in creating pseudopotentials here. We would need to have Neil Ashcroft on the line.
Thank you.
It gives some idea at least. Yeah. Could also have could also be useful if you wanted to decide if there's core-core overlap, for example. If it's longer than these differences, then probably not.
Hi, Martin. My name is Kim Bolduc. I'm a second-year graduate student from the University of Massachusetts Amherst, and I actually just had a question about this plot. Why does it appear that iron jumps up at the very low pressures?
There was one word that cut off there. Could you please repeat?
Sure. On this plot that you're showing right now, why does it appear that iron jumps up at very low pressures?
Ah, yes, okay. And yeah, so if I were to plot the individual atoms like I did before, these are rather smooth. They start high and then they go low, but they're interpolated between, say, 30 different explicit calculations. And then here we're comparing two interpolations. So there are some wiggles here, and these wiggles are not really physical. So there's some higher order polynomial that we've used to fit this. And so, for example, this little wiggle here, I wouldn't, say that means anything. So yeah, I would have to look into exactly if this is a wiggle or something physical. In general, I would trust this method less in the very, very close here, because there's much more happening to the radii. There's a very sharp contraction. But yeah, we see that. I should have actually mentioned this, because we see the same thing here in nickel and palladium, right? These ones, they don't exist. These little humps here, they are only from the interpolation. These are smooth curves when you look at the individual atoms. But when we want to do, just when we coded this comparison here, we want one to be flat and the other one to be relative. So it's a computational artifact. Yeah, good question, thanks.
Martin, you mentioned a few minutes ago core-core overlap, and so I'm wondering if it may be of interest to look beyond 300 GPa. There are plenty of transitions that are either predicted and in some cases observed up in the tens of megabar pressure range, and in the elements you have very dense electrides. Of course, the electrides happen at lower pressure for some elements, but even carbon and aluminum are predicted to be electrides at very high pressure. So I'm wondering if you could use this approach to rationalize what comes out of density functional calculations for the sizes of the atoms in those unusual structures at much higher pressure.
Yeah, maybe. One thing is that I'm a bit skittish of taking this too far, since we've validated it up to 100 GPa. So I trust it fairly well up to there, and then we push it to 300. So, but yeah, in principle, we can calculate any pressure here. We went up to 5 terapascals for beryllium just for fun of it, and it didn't turn into a p-block element. But you mean to just essentially quantify the size of the core and so on, or?
That's right. Try to understand more chemically, why these structures may form. They just fall out of DFT type calculations, structure search calculations, for example. But it'd be nice to maybe understand it at a more fundamental level or an atomic level in terms of the size of the cores and so on.
It could be done. I mean, we would have to. We would have to evaluate or validate the method, maybe possibly reparameterize a little bit. I'm not sure, but then make sure we have meaningful data, and there's no limit essentially.
So
convergence might be an issue at some point. Yeah,
it's Roald here. So a couple of comments. One thing that's underway is another way of getting an atom radius under pressure, and that is from Mao Sheng Miao's helium compression model. It's something that he and his group are doing. The interesting thing there is that he also has the compression of what we call an interstitial quasi-atom, that is an electride center. So we can compare when an electron would switch over from an atom to one of these. So that's one thing. And also a third comparison underway, and that is the group of Yan-Ming Ma, is actually a calculation of the radii of bulk matter in its favored state at 100 and 300 GPa. And we have some experimental numbers for that, but those experimental numbers don't tell you about where the electrons are. So we will eventually look at intercompare the non-bonded and the bonded ones, and that'll be an interesting comparison. Another point about just in general about the physics underlying this, and that's relevant to Russ's point about maybe looking at higher pressures. The basic physics here is that all orbitals that do not have a core to be orthogonal to, that means 2p, 3d, 4f, 5g, that's enough. Those orbitals are going to be pretty flat with pressure. And whereas S and P orbitals, if like 2s or 3s or 4s or anything like that, they have a core, and so they cannot be compressed. Their energy, they resist compression. They can be compressed, of course. So they go up, and that is where the lithium transition comes and where the potassium transition comes from. So in fact, beryllium and boron and carbon will also undergo a 2s to 2p transition, just at a much higher energy, a much higher pressure. And
well, we'll see. Right?
Out of range,
they are
out
very,
of range.
very similar in size. Yeah.
Yeah.
So we did look for them actually, and it's a bit. It just may be a coincidence that it happened for lithium and not for beryllium, but it's.
No, it's within that range. 300 GPa is just wasn't enough.
We actually thought about compressing individual electrons as well. We might do that for some electrode comparison. It's a little bit.
Great, thank you. Michael Hu, do you have a question?
Hello, hi, this is Michael from APS. I have a vague question. How do one think this, related to bonded atoms? Like, how do this will help us understanding like bonding maybe?
Well, I don't want to push this too far, right? To me, it's a relative measure, and they should not be expected to be more useful than normal van der Waals radii under normal conditions, which don't. I mean, they relate into bonding in the following sense: if you have an atom-atom distance from an experiment, and if that distance is shorter than the sum of these non-bonded radii, then you can expect that there should be some bonding interaction. That is the general way of thinking about it. But other than that, these radii are not related to bonding or structure. So, which is also, I mean, that's a blessing and a curse. It's nice because it makes life simpler. It's supposed to be simple, because then you can get quick ideas. Not sure if I answered here, but not a very strong relationship to bonding. For that, you have to.
I see. Yeah.
Spend more time.
It's a vague question to start with. Thank you.
That's a good question. Thank you. It's bonding is what matters in the end. So and getting bonded radii are harder, because then you have to consider which chemical structure do you relate to. So if you have many phases and many different pressures, what is, maybe you can average over many structures and get bonded radii then. But then the bonded radii to which elements, you can bond one atom to many other atoms. So it becomes much harder to estimate bonded radii.
Yeah.
Yeah.
And now the pressure is going higher and higher, and then under these circumstances, even the concept of like orbit, right? Orbitals and all that is is causing the question. So, but ultimately it's the electron density, I guess. So.
Yeah, and at least that seems to work out quite well here, that the definition is based on the electron density. The electron density is also the only way that we interact the atom with the surrounding. So that's what is understandable.
There's one more question from Jay. Do you want to ask that?
Yes, thank you, Martin. I was hurried to ask question at first time. And this question is the same as related to the Michaels. And we know cerium and aluminum are far apart, but under the pressure, they make intermetallic compound. So those kind of cases can be explained by your calculation. And can we kind of predict where and why and which pressure range some are formed, something like that?
I think that's another great question. You have a lot of good questions in this setting. I mean, you can get some idea, I think. I mean, to get the alloys, you'd ideally want to have atoms with similar sizes, if I understand correctly. And different atoms have different similar sizes under pressure. So here again is the 300 GPa one. And all of a sudden, chromium, magnesium, iron, and cobalt, they all have the same size, essentially. You asked about cerium and aluminum, was it?
Yes.
Yeah, so they differ by 0.1, and they differ by 0.4. Yeah, hard to make any specific conclusions there, but one can plot these and see how this relative change is different from other combinations, and at least argue from atoms being similar sized or not.
Mm-hmm.
But of course, no one has used these for that yet, so interesting to see exactly how useful they are.
Thank you, Martin.
Thank you. Thank you.
Any more questions? Well, if not, let's thank Martin. That was an excellent talk, and thank you all for joining us.
Thank you so much. My pleasure, Ross. This was great.
Okay, have a good evening.
Good evening.
Thanks, Martin.
Great seeing you. Okay.
Be well.
We should talk soon.
Yes.